Welcome everyone. Welcome to Parthibo. So here we will be trying to understand the frame of reference, the concept of inertial and non-inertial system by exploring the fundamental perspective from which we observe measure motion in physical world. So in physics, the concept of frame of reference is very important. Without it, we can't go on. So what is a frame of reference? It's a very easy concept and we can understand it very easily. So, a frame of reference is the viewpoint from which motion is observed and measured. It's the coordinate system that defines at rest versus in motion, whether a body is in rest or is it in motion. It always compare with certain things or certain object, and that comparison, the object that we take for comparison, that object is known as frame of reference. For example, we are living on earth, so most of the cases we take earth as a frame of reference. We take earth as our frame of reference, and whatever motion we observe in sky, we always observe that motion with respect to the earth. So different observers can see the same event in remarkably different way depending on whether they are moving or stationary relative to the move action. So understanding frame of reference is essential for grasping relative motion. So a cornerstone concept in classical physics and relativity. And all of you have heard about Einstein, right? And he's famous for his special theory of relativity. It's nothing but concept of relative motion. That means whether a person is moving with respect to us or not, mostly whether we are in motion, whether we are in rest, whenever we try to measure, try to understand anything, we always take ourselves as in rest. For example, let us say you are inside a train. Now, with respect to you, all the thing outside the train, outside the moving train, actually moving, and that with respect to you inside the train itself is in rest. So in that case, the train become the frame of reference for your observation. So whatever thing you observe, taking the train as in rest or as frame of reference, and with respect to that frame of reference, everything is moving outside the train. Similarly, a person sitting on a bench on a in a railway station, and that person observed that you are in motion because with respect to him, that platform is his or her frame of reference, and with respect to that frame of reference, the moving train are in motion. So with respect to the platform and also the person sitting on the bench on the platform, in the platform, the train is in motion. So it's a concept, it's a very relative concept whether a thing is motion or at rest. It all depends on what frame of reference we are talking about, or from which frame of reference we are observing anything. So this is the actual foundation of physics, this frame of reference. Now we are talking about inertial frames and non-inertial frame. Okay, here is the inertial frame. Also there is non-inertial frame. So what is inertial frame and what is non-inertial frame? Okay, mostly inertial frame, it's closely related to Newton's law of motion. Newton's law of law of motion. Okay, so how it is related to Newton's law of motion? Mostly inertial frames are those moving at constant speed. So before we go to how inertial frame related to Newton's law of motion, first we should have a clear idea what is a inertial frame. So mostly, let us say we are taking a three-dimensional coordinate x, y, z. Okay, now with respect to this coordinate we are considering another coordinate. Okay, another coordinate, let us say this is x dash, y dash, z dash, and this is moving with a velocity v, constant. Okay, constant, and this velocity is relative to this thing. Okay, this is the reference frame for this another reference frame. How can we say that? How can we actually explain this thing? For example, let us say this is the coordinate of earth, and this is a car moving with constant velocity. So with respect to an observer at O, this car moving at constant velocity. Now whatever thing happening inside it, those things take the car itself as a frame of reference. So the observer can see all the Newton's law is applicable for this frame of reference. That is, whenever a frame of reference, whether it is in rest, v equal to constant means v equal to 0 also be a value, right? So whether a frame of reference is in rest or is moving with constant velocity, then uh, it is called inertial frame. So inertial frame are those moving without acceleration, but it may or may not have a constant velocity. So in these spatial frames, Newton's law hold true without any modification or correction. What are those Newton's law of motion? There are three law of motion, right? So one is related to first law, that is inertia related, object at rest remain at rest, or a moving body always move in a straight line without changing its direction if there is no external force. That is the first law of motion. And the second law of motion state that if there is a force acting on a body, then rate of change of momentum will be in the direction of applied force. So let it be, mainly we'll be focusing on Newton's first law. So Newton's first law, it is related to inertia. So all inertia frames move uniformly related to each other. So whenever we talk about inertial frame, those inertial frame, either they will be in rest, they will not move with respect to each other, or even if they move, they must move at constant velocity or uniform velocity with respect to each other, and only then there will be no mysterious force appear out of nowhere. For example, a passenger in a smoothly cruising airplane feels no acceleration force, just like being at rest on the ground. But the person observing outside the aeroplane, he can see that aeroplane is moving very fast. So the person inside the aeroplane, for him the plane is act like a frame of reference, and with respect to that frame of reference he is at rest. So that's why he don't feel any types of force. If that plane move with acceleration or deceleration, then only then can he feel the force. That's why when the plane take off and when the plane land in the in the airport, you will see they advise you to attach your seat belt. That is because at that time a lot of acceleration and deceleration happen. That's why a lot of force act on you, act on the person inside the aeroplane. Now, what is non-inertial frame? Non-inertial frame, actually the acceleration, related to acceleration, or the if the frame of reference is not moving with uniform velocity, or let us say it is moving with uniform speed but not in velocity. Velocity means there will be no change in direction. uh, for example, here you see it is rotating around, rotating, right, rotating platform, and even if it has a constant speed, it is always changing its direction. So that's why there will, this also can't be considered as a inertial frame. So non-inertial frame, how we define that? Non-inertial frame are accelerating or rotating relative to inertial frames. And in this case, this platform is the rotating frame, and the earth itself on which it is rotating, that can be considered as a inertial frame. Okay, so what is the extra thing come due to the presence of acceleration or rotation? You see, there we have to introduce some extra to validate Newton's law. And in these frames, Newton's law appeared to be violate unless we introduce those fictitious force or pseudo force or inertial force to account for the frame's acceleration. Right? So this fictitious force is very very important with respect to our respect to our calculation. Why they are very important? We are talking about their fictitious, they are not really are there, but they come due to the presence of acceleration, due to the different frame of reference, right? So why should we learn them? Why should we learn about non-inertial frames? Actually, there is a reason. We are living on earth, right? And earth is not at rest. It is rotating around its axis. Also, it is rotating around the sun. So, earth, whatever thing we see outside earth, is those things always can be taken as non-inertial frames. So why those things observe in non-inertial frame because Earth is not in not at rest. So that's why whenever we observe something, those fictitious force come itself in our observation. So if we don't remove those fictitious force, if we don't consider those fictitious force, we will not get accurate result. So there are some example: braking car, passenger feels pushed forward when vehicle suddenly deaccelerate, right? That is also an example of acceleration, deacceleration actually. Rotating merry-go-round object appear to curve outward due to the rotating reference frame. So Earth's surface, our rotating planet, create Coriolis force that influence the weather pattern. For I think we have already known that the cyclone rotate anti-clockwise and clockwise in southern hemisphere and northern hemisphere. The rotation of the cyclone is different in two hemisphere. That is actually happened due to the earth rotation and the effect of the fictitious force Coriolis effect actually responsible for the rotation of cyclone in earth. Two different types of rotation happening in south hemisphere and north hemisphere. Now, let us uh, talk about the bowling ball in the track, a classic frame of reference thought experiment. We'll be discussing about this. So, explaining how motion depends on where you are standing and why physics looks different from different perspective. So, let us begin the setup. So, bowling ball in a moving track. So there is three condition. One is the initial condition. A bowling ball sit peacefully on the floor of a track cruising at constant speed. Constant speed instead of constant speed, we should say velocity. Okay, constant velocity down a straight highway. Second scenario, the acceleration scenario. What happens when the driver suddenly hits the gas? Does the ball roll backward or does it accelerate forward with the track? We will be finding out very soon. And there is a third scenario. What is the third scenario? The vertical toss. If someone tosses the ball straight up while the truck moves, where does it land? Now, this answer depends on who is watching. Is it the person inside the truck or a person outside the truck? So let's talk about the person inside the truck. So the ball's perspective. So shared velocity inside the truck, the ball initially shared the truck's forward velocity, making it appear stationary relative to the truck floor. Okay, it is in a state of rest with respect to the truck. When tossed straight up, the ball appears to rise and fall vertically, landing back in the thrower hand, just as it would in a stationary room. So for the person inside the truck, there is no force, no motion actually acting there, and everything is happening just like whatever we do in land in a state of rest. Everything happening like that. And backward roll, if the truck accelerate forward, the ball appears to roll backward because it resists. Why this happen? Because it resists its state of rest or change in motion due to the inertia, right? So sudden acceleration means there is an external force and the ball tried to stop the influence of that external force. So ball remain where it is, or ball try to maintain its velocity according to Newton's first law. And as a result of that, as the car, as the truck increases velocity, it moves faster, but the ball remain in motion at the initial velocity. So that's why it appeared that the ball is rolling backward. Actually, ball is not rolling backward. Ball is remain the same position or continues the same velocity, but the truck moving faster now. Now, what will be the person outside the truck with respect to him? What is actually happening? So, the roadside observer view. To stationary observer watching from the roadside, the ball trajectory is a graceful parabola, not a simple vertical line. So, uh, when tossed straight up inside the truck, the ball actually moves forward through space. So, whenever move forward and it landed in the like that, okay, and the person is moving from here to here due to the motion of truck, okay, and it's moved like this. So this is the observation that a roadside observer see. Clear? But the person, for this person, what is the observation? He will see that ball is moving upward then coming downward. This is the observation of this person, okay. So this one is the roadside observer. This is the truck inside the truck, and with respect to this person inside the truck, this is the observation of the motion of the tossing ball. So this pass perfectly illustrate vector addition. The ball's motion is the sum of its vertical velocity and the truck's horizontal velocity. What happened here? This is the velocity of truck and this is the velocity of the toss. So as a result of that, combination of that, a resultant force is act like this. Okay, this is the combination of, let us say this is a C vector and C equal to V plus U. Okay, and due to this action of this force, the person who is seeing outside, he see a parabolic path due to the influence of these two velocity. On the other hand, the person inside the truck, he only observe this velocity, uh, because for him this is zero, because he never able to observe that velocity. So different frames, different description, but same physics. So from outside, physics tells a richer story combining multiple velocity components simultaneously. Okay, so uh, this is a setup. What happened? First of all, from roadside inertial frame, so the person sit in the roadside, that is the inertial frame. The bowling ball continuously move at a constant velocity with the truck, while the truck deaccelerates beneath it. Okay, Newton's first law perfectly explain the motion. No force act on the ball. We have to consider no force act on the ball, no frictional force or any air resistive force. Okay, and from the inside the track, non-inertial frame, the ball appeared to accelerate forward without any visible force pushing it. This mysterious motion required introducing fictitious force to make sense of the observation. So who is actually observing the fictitious force? The person in non-inertial frame. And who is the person in non-inertial frame? The person sitting inside the truck, because after brake the truck deaccelerate. So as it deaccelerate, we see that the ball accelerating forward, but actual story is that ball is moving on its own space, but the truck decreasing its velocity, or the car deaccelerate. So person who is inside the truck, he never able to observe that deacceleration. So that deacceleration automatically add up to the ball as acceleration. So for the person, there must be a force acting on the ball, which force forcing the ball to accelerate. And this force is known as pseudo force, or a fictitious force that has no real um, existence for a person outside the non-inertial frame. For a person in inertial frame, uh, there is no pseudo force, but for a person inside the non-inertial frame, pseudo force is very real. So Newton's first law and inertia in action: a object at rest stay at rest, an object in motion stay in motion with same speed and direction unless acted upon by an external force. So inertial state, the ball moves forward at constant velocity with the truck experiencing no net force. Truck accelerate or deaccelerate, accelerate or deaccelerate. The truck floor moves forward, but the ball inertia restrict the change in motion. Okay. So apparent backward motion inside the truck's acceleration frame, the ball appeared to roll backward, but it is really the truck accelerating forward around it. So before this, we are talking about deacceleration, but if the truck accelerate, even then we'll see that somehow the ball is pushing backward. So there is also a pseudo force acting there. So that's how it work. So what will be the real world demonstration? Throwing a ball up in a moving truck. Set up position camera inside the truck moving at steady speed. Prepare a toss ball straight upward. Release the ball vertically with a no horizontal push. Watch carefully as it rise. Ball land back in the thrower hand, confirming it retained the truck horizontal velocity throughout the flight. If that doesn't happen, it's accelerating or deaccelerating, whatever it is. So the simple demo makes abstract frame of reference concept tangible and memorable for learners. So you can do that. Toss anything and see whether your car is accelerating, whether your car is deaccelerating, whether your car moving at constant speed. So fictitious force, this apparent force has no physical source. They arise purely due to the acceleration of the frames of reference itself. Yet they are essential for applying Newton's law inside non-inertial frame. So first of all, centrifugal force. What is centrifugal force? Uh, the apparent outward force felt in a rotating frame, pushing the object away from the rotating axis. So it's a pseudo force. Centrifugal force, it's is a pseudo force. Actually, what force act in a rotating surface or a rotating object? Actually, there is a centripetal force. It act just the opposite direction of centrifugal force. Centrifugal force act outwardly. Centripetal force act towards the center. They have the same value, but their direction is opposite to each other. Okay. Next, Coriolis force deflects moving object in rotating frames, creating characteristic spiral of hurricanes. We are talking about storm that is happen due to the Coriolis force. So these forces emerge from the coordinate transformation equation between frames. So we'll be talking about that later. So velocity and acceleration, key transformation equation, understanding there are a lot of things happening there. So we'll be doing that later. So real world impact, weather engineering, understanding the frame of reference isn't just academic, it has a profound practical implication across science and technology. Weather prediction, engineering design, Earth's rotating create Coriolis force that shape the cyclone, hurricane, and global wind pattern. Meteorologists must account for our non-inertial frame to forecast accurately. Nowadays, the satellite can take picture from the space, and by analyzing those picture, we can predict the pattern, how the cyclone will form, how the cyclone will go. We can predict all those things. So spacecraft trajectory calculation use inertial frame of precision, while mission control account for Earth rotation and tracking from the ground. So everything is related to frame of reference. Without perfect calculation, we can't able to go in space navigation. For recently, we are talking about Chandrayaan mission of our ISRO, and why various countries failed, because there's some calculating error. We have to be accurate, and Indian scientists are accurate for landing, for the calculation, and there play frame of reference very important role. Without calculating the inertial and non-inertial frame of reference, we can't able to land on the moon surface. So that's the importance of frame of reference. By learning them, we can predict what types of force there will be acting on those things. By predicting those calculation, we can plan our landing. So why frame of reference matter? From Galileo to Einstein, understanding reference frame revolutionized how we describe the universe. This principle explains why passenger in a car, airplane, or train experience motion differently than outside observer. So mastering frame of reference open door to spatial theory of relativity, orbital mechanics, and beyond. So next time you are in a moving vehicle, toss something gently upward and watch with where it lands. You are witnessing the fundamental physics in action, the same principle that govern planets, satellite, and the cosmos itself. So choosing your frame, convenience, and clarity. So physicists strategically select reference frame to simplify problem solving and gain insight in physical system. Inertial frame prefer the for fundamental laws and theoretical clarity. Newton's law apply directly without modification, making analysis straightforward. On the other hand, in case of non-inertial frame, useful for describing everyday experience and analyzing rotating system, often match our intuitive perspective, even if requiring the additional mathematical terms. The art of physics often lies in choosing the reference frame that makes the problem easier to solve. So, if we summarize the thing that we have learned, so first thing, inertial frame, non-inertial frame, and master the concept. Inertial frame, Newton's law, works straightforwardly with no extra force required. Non-inertial frame require fictitious force or pseudo force to explain observed acceleration and motion. And master the concept, answer the understanding the frame is key to classical mechanics and beyond. Thank you for everyone. Thank you everyone. That's it for today. Good night.